Great. So Sam Mugel is a founder and is the CTO of Multiverse Computing. He is an expert in quantum computing and quantum machine learning. He has a PhD that was jointly awarded by ICFO from Spain and the University of Southampton in the UK. Sam was formerly a computational physicist at Corterio in the UK, a scientific advisor at the Quantum Revolution Fund, and founder and CTO at Ground State Consulting. So welcome, Sam, and thanks to the Multiverse team for doing this today.
Thanks for the kind introduction, Susan, and thanks for having me. It's a great pleasure to be here again. Great. So as Susan said, I'm CTO and co-founder of Multiverse, and you have my contact details here. So if you have any questions after the talk or any inquiries, don't hesitate to get in touch. To give you an idea of what we're going to talk about today, I'll give you a brief overview about what is Multiverse and what we're building. And then we're going to dive in deep to a case study that we've been working on with the Bank of Canada for the last 8 months or so, which is about using quantum computing to predict the usage of cryptocurrencies. So really interesting topic. I'll start with some motivation, describe the economic model to you, and then we're getting into the really fun stuff and telling you how we solved this thing and what conclusions we can take. The talk is thought to go from quite a high level to, we'll get a little bit technical at the end. If you get lost, absolutely no worries, we'll bring everything back with questions at the end. We'll keep about 20 minutes at the end of the talk for questions. So with that, let me start telling you about Multiverse. So we're a team of about 50 people distributed between Spain and Canada. Some really great physics talent, some excellent domain experts, and we're actually hiring at the moment. So if you're interested in participating, really don't hesitate to get in touch. The best email address to write to is up here. And some credentials, we were featured by the Boston Consulting Group as one of the startups that's really doing impactful work in quantum computing for industry. So that was really great. And we're also on the McKinsey Technology Council. So there's, I'm not entirely sure how many of us, 20 or so, and we're discussing basically where is quantum computing going to go and how much value is it going to create for industry in the next few years. So really fun group of people. Great. With that, I'll tell you a little bit about, give you a really brief overview on some projects that we've got going on at the moment. So where we've been really successful is collaborating with some really big names. And so these are all paying customers for us. You recognize Bosch, perhaps Crédit Agricole, BBVA and CaixaBank, two major European banks. And obviously Bank of Canada, European Tax Agency. These are the projects that are open, that I can talk about basically. And you'll see we use a really big variety of backends. So D-Wave we've been working extensively with, and we've obtained some really impressive results with. And we also work with IBM, Xanadu, Alpine, IonQ. Those are two Ionic backends, Pascal. And we've got a whole battery of in-house algorithms that rely on tensor networks to accelerate HPC. So this is not TensorFlow, and I'll show you in a second what we can do with that. Our first big win that I presented here last year was our project with BBVA and CaixaBank, and we're currently building on that with an American bank. And so this is a portfolio optimization tool. We saw that this problem could be run very well on D-Wave. And so this is what I'm presenting on the right. We're seeing that using D-Wave, we were able to approach the efficient frontier much closer than these blue dots over here. And so for reference, this was a portfolio spanning 1 year with daily rebalancings. And our customer was able to, so Cachet in this case, was able to offer portfolios in the kind of like a high volatility, high profit corner of this blue cloud over here. So we were very, very happy with these results. And if you're interested to learn more, I invite you to look at the publication on this topic. In addition, and I've included a bunch of references at the end of this presentation. Just briefly to tell you about our work with Crédit Agricole. So this is the world's 11th biggest bank. And we are looking at exotic option pricing with them. This is a problem that all banks in the world have. It's a huge sink for computational resources. And an idea that came out recently was, what if we can use neural networks instead of using Monte Carlo that's traditionally used for this? This has one advantage, which is if you can change the details of your problem a little bit without having to run a whole new set of computations. But training is extremely difficult. And so our idea is, let's replace some of these layers by some tensor networks object. And we're finding some like order of magnitudes, like faster training. And so this is extremely exciting work, and we're bringing out a publication on this in a month or so. In addition, we've started having customers approaching us from outside of the finance industry. So we started with a really strong footing in finance, and then Repsol, which is an energy manufacturing company, approached us and said, hey, can we apply your models that you've been developing inside of energy management? And specifically, if a lot of people are producing energy, who should we buy from? How much can we sell for? And a challenge that we've been finding here is that a lot of the constraints are beyond quadratic. So we've been seeing that we can use tensor networks to address this problem. And finally, to mention our project with Bosch. So this is a multi-year collaboration looking at predictive machine maintenance and like manufacturer process optimization. And so we'll be looking with them at how can we apply quantum routines and tensor networks routines with the idea of putting that into production. So just to a final word about this. So you'll have seen that we're addressing a large variety of use cases with some big customers. And the idea is to provide a very simple interface for these non-quantum experts to be able to access our code through the cloud and then plug into all these different like backends, whether it's superconducting, photonic, ionic, neutral atoms, or like tensor networks routine backend. So that's kind of, in a nutshell, what Multiverse is and what we're building. Great. So with that, I'd now like to jump over to this case study that we've been working on with Bank of Canada, which is about applying quantum computing routines to predicting the evolution of cryptocurrency networks. The Bank of Canada did ask me to specify that the views that we're presenting here are not the views of the Bank of Canada in general, just of the people that worked on this study. Great. So to give you a little bit of motivation behind this project, there's an extremely hot topic at the moment, which is, could we use cryptocurrencies or CBDCs as alternatives to cash and banks, essentially? And there's a number of trade-offs that you have to think about if you're going to do this, which we're going to delve into a little bit later. To tell you a word about CBDCs, They are a digital money that's pinned to the value. So ignore it saying the Bank of England here. I got this image off of Google. But essentially, it's a digital money that's pinned to the value of your currency. So in our case, it would be the Canadian dollar. And that can be used for payments without necessarily going through banks. So this is really the idea of using crypto for payments and not necessarily as an investment. And this is really like what we'll be focusing on during this talk today. One topic that central banks are worried about is the adoption of cryptos as a means of payment could happen sequentially. And then you have the question of, does it matter in which order, and can policymakers help to foster crypto adoption? In addition, we're going to see that these things are controlled by game theoretic networks, and I can be forced to adopt a behavior that's inefficient for me. In this case, we talk about market inefficiencies. We have the tools to create a large amount of value, but we're under-exploiting them. And so can policies actually help to limit market inefficiencies? And in addition, we'll delve into as well, what's the relevance of privacy and digital costs to the adoption of crypto? So these are all like questions that we're going to be studying, and all reasons why we think this study is very, very interesting. Great. So let me dive into the economic model a little bit. So we're going to look at big N firms that are trading with small n others. So in the example on the right here, you can see I have how many? Eight firms. So big N equals 8, and each firm is trading with 3 others. So small n equals 3. And a crypto channel is established if the link has a value of 1. So basically, this player and this player are trading. And if the value of the link is 1 between them, we're going to say they're trading through a crypto channel. And if the value is 0, they're trading through bank transfers. I'll be using bank transfers and cash transfers interchangeably in this presentation. And so the problem statement for us is we want to predict which methods of payments players will choose to exchange money between them. And one thing that we're going to see quite rapidly is that the equilibrium states of this network are not necessarily optimal for everyone. So this is a really interesting peculiarity about these systems. And now for the rules. So if 2 players exchange crypto, this is essentially a contract between them. And to form a contract, player 1 and player 2 need to agree on this, right? So to form a crypto channel between 2 players, and this needs to profit player 1, and it needs to profit player 2. And the key quantity we're looking at, and that I'm going to come back to, is the utility in this case, using economic jargon. However, 1 player is sufficient to break a crypto channel. So if player 1 has a utility gain to breaking the crypto channel, or player 2 has a utility gain to breaking the crypto channel, then they'll go back to exchanging money through cash transfer. So just to summarize, we're looking at N firms. They're exchanging money with certain of their neighbors, and they have to choose between exchanging via cash transfer or bank transfer. They default to a cash transfer, but if they're both agreed, then they can form a crypto channel and exchange money via crypto. How do firms pick a currency? Well, they need to make a trade-off. The trade-off is between the cost of setting up a cash or crypto channel and their desire for privacy. And we're going to work with the assumptions that crypto channels provide a greater privacy. However, past the initial setup costs, crypto transactions are actually cheaper than bank transfers. And so all the relevant quantities here are the privacy sensitivity, the probability of privacy sensitive goods, the transaction costs. So we're going to look at the costs of a crypto channel, a cash channel, a bank fee, and also the setup costs. So that's just a whole bunch of variables that, that goes into these two terms up here. At this point, you could ask, okay, if a player sets up crypto, then clearly their desire for privacy is going to drive crypto, and the transaction cost is going to drive crypto. So intuitively, you'd expect either a player wants to trade cash with everyone, or a player wants to trade crypto with everyone. We're looking at identical players, so we'd expect this to like converge to one of two networks. Either everyone's trading cash or everyone's trading crypto. There's an additional behavior that makes these networks very, very interesting. And that is if there's danger of crypto taking over, banks can actually retaliate. So if we're seeing that cryptos are widely adopted, it's actually possible for banks to say, I'm going to put all the costs of bank transfers way down, and this is going to naturally lead to players wanting to have a mix of currencies, use a mix of currencies. And so the key quantity that we're going to be looking at from here on is the adoption rate. So this is the, for any player, it's the amount of people that they want to be trading crypto with, if that makes sense. So I'll show you an example of this in a second, but basically, if I'm a player, this quantity, the adoption rate, delta star, tells me how many other players I want to be trading crypto with. And you can see, without going into the economic model, the economics tells us that this is a really like complicated function of all these like quantities that go into the privacy and the transaction costs. I'm not going to derive this for you. We're bringing out a paper on this in a month or so, and this will be explained in detail in there. Great. So now to tell you a little bit about why we think that it's appropriate to use quantum in this case. So this is an extremely hard problem. The reason is payment contracts are cooperative. So these networks can lead to extremely complex behavior, and this behavior is controlled through game theory. Additionally, something that's really special about this system is that other players can force me to adopt inefficient behavior. So you get this weird situation where identical players can actually behave differently. And so there's an example of this over here on the right. So we're looking for stable states in my network, and I pictured three here. So all three of these states, once I'm in them, I cannot leave them. There's no transactions that like players would agree upon that would bring me to another network. So these are stables, but they're not optimal. So in this case, we have 8 players, each can trade with 3 of their neighbors, so small n equals 3. and delta star equals 2/3. So each player wants to trade crypto with 2 of their neighbors and cash with 1 of them. The global optimum is this one on the left. So you can see each player is satisfied they're trading crypto with 2 of their neighbors. However, these other 2 on the middle and right over here are also stable networks. So I can get locked into these configurations. And what you can see, for instance, on this one in the middle, is that the top and bottom players are frustrated. They have smaller gains than the market would allow for because they're trading crypto with no players where they'd want to be trading with 2 of them. So this is, these are also configurations that our model needs to be able to detect, and they're not globally optimal. Additionally, the number of network configurations is absolutely huge, and I'll say a word about that later on. Why do we think the quantum is appropriate? One of the reasons is that, so this is an NP-hard problem. We've seen that it can be mapped to the Ising model, but in addition, like what we're really trying to do here is to sample a space of solutions which grows combinatorially with the number of links. And so here we saw a really good fit for D-Wave's technology because this is exactly what D-Wave does. D-Wave takes a huge space of solutions and samples it, samples the optimal states. Sorry, not the optimal, in our case, samples the stable states. And I'll give you some intuition about how we do that in a second. So to summarize rapidly, so we have networks of players. For simplicity, we're looking at identical players. We want to find out who's going to trade crypto with who. And we've seen some examples of how players can be forced into behavior that's suboptimal for them. And the key quantity that we're really interested in is this delta star up here that's given to us by our economic model. Okay, so with that, let's delve into the quantum algorithm. So the first thing I'm going to do is encode each link between players to a qubit. So if the qubit is in state 0, then we have a cash transfer between both these players. And if link is in state 1, we have a crypto transfer between them. And so the network that's pictured in the top left up here, you'll see that player 1 and player 2 are exchanging cash, player 2 and player 3 are exchanging crypto, and player 3 and player 1 are exchanging crypto. And so I've taken a really simple, like 3-player toy example to illustrate this. And so the state of my network in this case is simply 0, 1, 1. Then the challenge is going to be for me, let's encode all networks, all possible networks to the QPU, okay? And finally, I'm going to penalize network configurations that have a lot of improving deviations. I'll tell you how we do the penalizing parts in a second. I'll just tell you about the improving deviations part. So this network has 3 configurations that I can go to with a single bit flip. So you can see 0, 1, 1 can go to state 1, 1, 1. So I've just formed a crypto channel between 1 and 2. And this is an improving deviation if player 1 and player 2 have a utility gain for forming this channel. In this case, I've marked this deviation with a cross to say this is not, they don't have a utility gain to doing this. Otherwise, I can break, for instance, the link between player 1 and player 3. And so this would be going from top left to bottom left. I'd be going from 011 to 010, and I'm allowed to break this link between player 1 and player 2 if player 1 or player 2 have a utility gain to breaking this contract. And once again, I've crossed this change out to show that in this toy example, this is not an improving deviation. Same thing for breaking this link between player 2 and player 3. And so in this case, this network in my top left corner has no improving deviations. And so I'd want this to not be penalized by my cost function. Is that clear for everyone? Okay, but yeah, just to summarize, so the statement of my QPU is mapped to a network configuration. I want to encode all networks to the QPU, and then I want to penalize networks that have a lot of improving deviations, leaving them. To tell you how we're going to do that is we're going to use this cost function over here. I'm not going to dive into details of what these three different terms are. I'll just tell you what they do. And once again, like this is going to be exposed in a great amount of detail in the publication we're bringing out. I invite you to like either read that or ask questions at the end of this talk, or email me with questions. So this first term over here is what we call the reading terms. So this is telling me, am I trying to create or to destroy a link? And so basically this is going to fetch the corresponding term in my utility matrix. And the utility matrix is given by the details of my problem. So basically by the data that I've fed into my problem. The second term over here is my constraint terms. So this is saying me, am I allowed to break a link given the utilities? So for instance, yeah, there's a link between player 1 and 3, and do either of them have a utility gain to breaking that link? Finally, the penalty term counts the number of improving deviations and penalizes is a penalty term to the energy if there are many improving deviations. So an interesting thing about this this cost function is that it's only constraints. Like the energy doesn't have a physical meaning in this sense. Now I'm going to show you this actually works. So over here on the right, still with my 3-player example, over here on the right, I've noted each node on this graph on the right is a network. So one configuration of my 3-player network, and there's 8 of them. So this is 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. And what you can see is if I start my system, for instance, in my configuration with index 0, then I have improving deviations that are these blue arrows that are sending me either to this network index 1, this network index 2, or this network index 4. And then these 3 nodes in green are actually stable, like there's no improving deviations away from this. And over here on the left, you can see the energy spectrum of this very small example. And what you can see is that the spectrum is gapped. And most importantly, these 3 stable configurations, the network 1, 2, and 4, are the lowest energy states. So we've verified that for this very, very simple 3-player example, this cost function that I presented earlier is actually penalizing all these nodes that have many outgoing deviations and is actually has as a ground state the stable networks that we're interested in. Great. So now that I've told you how to solve this on a quantum computer, I can tell you how we can use this system to make conclusions about the economy. So first, what data did we use? So the setup of our problems, we're going to look at a set of identical firms that we're going to call representative firms. Okay, so we're going to study an 8-player example. So we're looking at big N equals 8, and we're looking at a fully connected network. So this is small n equals 7. As I said, the key quantity is the desired adoption rate. So how many people do I want to be trading crypto with? And we've used some data from a survey that Deloitte has been running for the past few years. And we've said, okay, the adoption rate is simply going to be how many firms have intentions of using blockchain and what proportion of that use is going to be dedicated to payment. So simply that quantity times the other one. The scenarios we've considered are current. So this is currently how many firms can we expect to be trading crypto with other firms. And we found this to be 15 to 28% of their payment channels. And then we've considered 2 extra scenarios which are favorable to crypto, so with a higher delta star, and extremely favorable to crypto. And here we've gone to more than half of your payments go through crypto. The reason why we've considered these scenarios is we expect that as time goes on, the cost of adopting crypto is going to go down, and therefore we expect that as time goes on, the adoption rate is actually going to change with time. Great. So let's first look at the current state of adoption, which has every firm wanting to trade crypto in 15 to 28% of their payments. And this translates in an 8-player network. This translates to players want to form a single crypto channel, basically. And in this case, we're seeing there's only one stable state. So 8 players are going to pair up and form 4 isolated pairs. So, and in this case, everyone is happy. Everyone's found a partner with who to trade crypto. And so we're in an efficient market, basically. So, and you can see this from this graph down here. So this is, I've looked at each player. So on my x-axis are my player labels. On my y-axis are how many people is that player trading crypto with. And I'm seeing that on average, each player, so averaged over all stable states, each player is trading crypto with one other player. So we're at full efficiency. Now let's look at a more favorable scenario to crypto. So if I increase delta star to between 29 and 42%, players are going to want to form crypto channels with, on average, well, with 2 other players. On my left-hand side figure here, you can see that the average degree is actually smaller than 2. So looking at averaging over all stable configurations, we're seeing that players on average are not trading crypto with 2 players. And this is due to these these inefficient networks that are popping up, and you have you can see that cliques are forming that are inefficient. So for instance, in the bottom left-hand side network over here, player 3 is isolated from the rest of the network and hasn't found 2 partners to trade crypto with. So what we can see here is that as I've made my network less local, we're having inefficient cliques that are popping up. And there's already a really non-trivial lesson that you can take from this, which is don't delay your crypto adoption for payments, because as the adoption rate, this delta star quantity goes up, you might actually end up in a clique that's forcing you into an inefficient behavior. So already this very simple model is giving us some interesting conclusions there. Finally, we looked at a very favorable scenario for cryptography, for cryptocurrencies. And here we've gone to a system where players want to form on average 4 crypto channels. And here you can see that out of 57 networks that are stable, only one of them is efficient, which is the one on the left over here. And then all others, including this example on the right, have players being forced into inefficient behaviors. And so if you look at the average adoption rate amongst players, we're seeing that on average, players are only getting to trade crypto with 3 firms, whereas they'd like to trade crypto with 4 firms. So in a case where your adoption rate is very high, you're seeing significant market inefficiencies pop up. And to say a word about the scaling, so this is an example of a problem that actually scales super exponentially with your number of players. So the number of potential networks goes as 2 to the big N to the square, whereas the number of qubits actually only squares as n to the square. So to put some numbers on this, for n equals 8 players, we were looking in the simple example, in the first current scenario that we were considering, we were looking at finding the one stable state out of approximately 10 to the 13 possibilities. To put that in numbers, 10 to 13 seconds is the age of the universe, I believe. For n equals 15, and you can see for 8 players, we were able to do this with on the order of 300 qubits, more or less. For n equals 15 players, this would require more resources than there are atoms in the visible universe. However, we could solve this problem in theory with approximately on the order of 1,000 qubits, a bit more than 1,000 qubits. So this is actually a work in progress at the moment. What we found is that as we go to a higher number of players, constraints become really difficult to deal with. So we're still working on making a good use of the QPU to deal with this. And so over here on the bottom right, you have some results that we've been having with the D-Waves platform. So just for reference, if we were going to do a random sampling of the solution space in the current scenario, we're actually at 8 players, we'd need to run like just under 1 billion samples to find the solution. With Leap Hybrid, we're finding this in 100 runs, and with Kerberos, we're managing to obtain the current solution every time that we run this. So really interesting results. And just to conclude rapidly, so what we're planning to do in the future is heterogeneous players. So what if all players aren't identical? And here we're really getting into stuff that's like very, very difficult to do classically. And so this is something that we're looking at doing with quantum computing. Having more complex non-local interactions. So you could imagine scenarios where, for instance, I'm a late adopter of crypto and my utility to adopt crypto will actually go up if I see that a lot of people in my network are adopting crypto. And so here you're really getting into interesting like utility functions. Additionally, something that we're looking at the moment is finding cycles. You can have really interesting behaviors where, for instance, if banks increase, like if banks drop their transaction fees, if they see the crypto is being widely adopted, then maybe people abandon crypto, but then banks put their fees back up and people re-adopt crypto. And you get locked into this cycle and there's no stable state. This is really, really difficult to do classically. And we've been doing lots of work on this and didn't mention it, but it will go into the publication. And finally, can we develop similar algorithms for more challenging financial networks problems, and maybe looking at using like either tensor networks or different hardware as well for these like more complex utilities. And to conclude, I think the first thing that I'd want to say is that I think this is a really interesting example because it's an example of like simulating the economy is something we are notoriously bad at doing. And here we've got classically, and here we've got an example of like, wow, okay, like quantum computing is actually going to enable us to do entire new things, like create value in places where we haven't been able to create value in the past. And so rather than just accelerating something that we already know how to do to some approximation, here we're really creating like entirely new value. But what we've seen in the study is, so as as the cost of crypto payment drops, firms will want to establish more crypto channels, and this will lead to crypto being adopted in jumps, and that firms that are the first to adopt will likely be the ones to benefit the most from crypto usage. In addition, we've seen that crypto adoption can be limited by coordination failures. So this is why called market inefficiencies as well. And so this leads to inefficiencies and under adoptions of crypto, and particularly these cliques that I was talking about. In the current scenario, everyone is happy and the efficiency losses are likely to be a minimum. But as crypto becomes more attractive, we can expect to see more coordination failures and even up to like 24% economic losses due to these failures. So that's been my talk. I hope you've enjoyed it. And it's been really great to have you here. I've included a bunch of references that are interesting at the end of these slides. I refer you in particular to the keynote we gave at Qubits 2021, also hosted by D-Wave, where we went into a lot more details about the model. And if you want a copy of the slides, or if you simply want to get in touch, really don't hesitate. You have my email down here. And with that, I think let's jump to questions.
Great. Thank you so much, Sam. And Sam Palmer, if you want to turn your video on so you can be available to answer some questions. We've answered some during the talk, but we have some that we'd like to ask you live. What's the difference between CBDC and money that's deposited on my bank account, which I can control via internet banking? To me as a user, they both seem to be equally digital and both have the same value.
Yeah, so I don't know an awful lot about CBDCs. I'll state something about it, and then Sambama, if you maybe want to take over. Essentially, when you have money, digital money on your bank, you're still relying on a third party to make a bank transfer. So you're still relying on the bank and their ledger to validate that, for instance, I've given money to Sam Palmer. However, with a digital currency, I'm able to make this payment without relying on the bank as a third party. Sam, is there anything you'd want to add to
that? Yeah, so I think it's I think it's just, you got to think of it as it's a cryptocurrency basically controlled by the banks. So it's formed on blockchain where it's going to have a value. It's not like the cash amount you see in your bank account. So it's kind of a different concept. And as Sam said, it's kind of what they would be used for internal transactions between central banks.
Okay, next question. In the QBO formulation, should we not introduce a Lagrange constant to the constraints?
Absolutely. Absolutely. I swept those under the rug. Every constraint comes with its own Lagrange parameter.
But I think in this application, it's not as important in other applications because to get our solution, we want all the constraints to be satisfied. Whereas if we have a Lagrange constant, we're saying we want it to be satisfied to some degree. So in our case, because we want everything to be satisfied, we can get away with not having them. Obviously, if we have them, it kind of changes the importance of them when we're getting very close to optimal solutions, but not the optimal. But in the end, the optimal solution is where all the constraints are satisfied.
Okay. Is the assumption of equal players realistic? Both chains, CEXs, and banks have way different transaction volumes and levels of adoption.
Yeah, so this is a really good question. Did we actually do any work on like heterogeneous players?
So that's something we haven't looked at yet. It will be, I think it hopefully should be going in the paper.
Yeah, I think like at the end of the day, I think economics people, I don't know how you say that, and physicists like tend to think in very similar ways of like, let's take a vastly oversimplified like system and let's make some conclusions and then let's see if those conclusions hold up as we add like complexity to the system. I think, but I believe that to some approximation, the really important thing in this case was how much do firms value their privacy, and we have allowed for firms in this model to trade goods that require different privacies. So I believe that it's not that impactful that all players are identical. Would you agree with that, Sam?
Yeah, I think that's a fair conclusion. But I think also once we would start adding heterogeneous players, things like, as Sam mentioned, these cycles, which are very difficult to identify, they actually come more into play into the dynamics. So we do see with homogeneous players, the dynamics can be a little bit simplified. So the next step is the heterogeneous players. And yeah, that's when we would start to get these even more complex problems. And as Sam said, I think this is something which is going to go into the paper as well, because it's a very interesting problem and very challenging.
Okay, next question. Could this problem somehow be formulated as a max cut or maybe max below min cut?
So the difficulty with that is to do with the rules. So to embed it directly as a graph, it's hard to do that because we have these anti-symmetric rules in how the links are formed and broken. So obviously there's the constraint where there's the or condition where links can be broken by one player or like they can be made by both of them. And you can't actually really capture that behavior in traditional graph theory. So that's why we've used the D-Wave machine to actually be able to model these interactions dynamically, because it's actually a dynamic network formation.
Okay, great. How do you know that the solutions you got are better? What is the metric you use to assess that?
Well, in our case, it's actually fairly easy to verify if a network is a stable network or not. So just by inspection, we're able to say, are these solutions valid and are they stable states? Better in what sense? We were able to go to larger systems, and we were able to verify that the conclusions that we derived were valid, basically.
Okay. Do you have any GitHub repository with the toy model?
No.
Okay. All right. I think we have time for one last question here. For n values larger than 8, does the 15 to 28% delta plus range also result in the best efficiency?
This is a great question. So 15 to 25% in a fully connected network leads to each player has 7 channels and they want to trade crypto with one player. If you add a new player into that, now each player is trading with 8 channels with 8 other players. And so it's likely that the step for players now suddenly wanting to trade with crypto with 2 other players is going to be a little bit lower, if that makes sense. So for instance, I can't remember the exact numbers, but we saw the delta star until delta star equals 25% something. We want to trade crypto with one neighbor, but maybe if you add an extra player, you'd find that cutoff is at delta star equals like 21%. I don't know, I'm inventing this. And so you'd start seeing, as you add more players into it, you'd start seeing maybe these cliques appearing earlier, basically.
Okay,
So,
well, I think we're out of time. We do have some questions that we will send answers via email. Again, this has been recorded. We will post it to the D-Wave YouTube channel the next day or so, and we will send out a follow-up email to everyone who registered and attended with links to the slides and to YouTube. So thank you so much, Sam and D-Wave panelists as well. We look forward to seeing everybody at a future webinar. So make sure that you opt into our emails so you can find out about future events. Great. Thank you so much, everyone. Bye-bye.
thank you.
Bye.